Yeah.
It's a senior costume. So it's cool. It's fun. It's fun class.
I went to school. I know that.
And students don't do anything.
Okay, ready to get started. Can you hear me in the back? Yes? Great. So I am going to introduce Dr. Lynn McMurdie. She is an associate research professor at University of Washington, and she has such an interesting background. So she got her BS at UC Davis in California, where she grew up in California, and then she spent her grad school years at University of Washington with Grant in the same research group, and John. So there's a long history here. She did her postdoc here at Sims, so she's very familiar with this area and Madison. And then she was at Washington for many years as a research scientist and award-winning lecturer teaching classes. And what year did you come? I should have written this down. I should remember this. 2017.
Yeah.
Becoming a research professor. And so Lynn wears a lot of hats, and over the years she's been leading lots of field campaigns. And so her first stab at being a project manager was for the Olympics campaign in Washington. And then she was the forecast coordinator of Relámpago in Argentina, so from going to northwest, mid-latitude to severe weather in Argentina. And then she's here to talk about impacts, where she's the lead PI for a multi-year field campaign studying snowstorms. And so Julia wanted to invite Lynn after seeing her present at the Madison, was it the Madison Collective meeting that happened last summer on impacts? And we're very excited to have Lynn here. And finally, I always like to talk about what they like to do outside, you know, whole human beings. And so when Lynn's not directing field campaigns, she loves to garden, she's in the mountains, and she makes the absolute best jam of anyone I've ever known. So if you want orders, you should probably take them now. So, all right, go ahead, Lynn, thanks a lot. Yeah.
All right. So I was given this microphone, but I do tend to yell, so I hope I'm not yelling too much. And I'll try to figure out how to attach this to myself. I first want to thank you, Julia, and everybody for inviting me. It's such a thrill to be here. I've had such a great day visiting with old and new friends. I've always loved it here in Madison, and it's just, we've got a great group and a great science group here too, so I'm really, really thrilled to be here. As soon as I can figure out how to attach, there we go, pocket, got it. All right, so I'm here to talk about snowstorms. So the title is really long because our acronym IMPACTS, which is short, has a really long translation. Investigation of Microphysics and Precipitation in Atlantic Coast-Threatening Snowstorms. And this is an example one that we actually flew in the background. I want to make a shout out to Deputy PI. So when we first originally decided to do this, you have to write a big grant, a big proposal, and Jerry Heinsfield and John York, and Scott Brown and I wrote that. John Yorks came in later. And I wanted to also give a shout out at this point to my team at University of Washington. Some of the results I'll show here are from them. But I also don't want to forget the entire impacts team, science team, which is actually quite large. Every time somebody asks me how many people are involved, I kind of look at them blankly, in the hundreds? I don't really know how to count them all. So several institutions are involved, like Stony Brook, SUNY Albany, University Illinois, Champaign-Urbana, Oklahoma, North Carolina. I probably forgot about 10 other ones. So it's a big group of people. You'll see why. It's a fairly extensive field campaign. So I probably don't have to convince you all that snowfall is important, but I thought I'd take a few headlines, and why it is out of focus is sort of a problem. Do you know why it's like not so clear?
I don't understand why it's showing up as that small screen. It's like it's letterboxing it somehow, and I don't know.
Yeah. Okay, pretend you could read all that. That might affect other things we're seeing. So I will have to like do the song and dance. Pretend it's really clear. So those are headlines. You can't read them. Events that happened in the upper Midwest here this year and last. And so snowfall is beautiful. I mean, it's like hitting the trees, but it's also really hazardous. And like the truck that's off the side of the road here, and people have to shovel snow, etc. So it's hazardous, especially for travel and for keeping schools open and such. But snowstorms and the snowfall within them varies widely. So when you see like satellite pictures like this, you see a really large area of cloudiness. And you think, oh, it's snowing everywhere. Oh, maybe it's raining or snowing everywhere in there. But the truth is, it's not like that at all. It's much more mesoscale. Wow, I made a big X. Okay, this is very confusing. Why? Like we're both puzzling about the incompatibility between my machine and this. Okay, so the snowfall within here, it varies a lot. So you can see that the clouds have different tops to them. And when you look in terms of radar reflectivity, you see the very uneven distribution. It's often in banded structures. We could call those snow bands. So there's a primary one right here with a region of high reflectivity and then much lower on each side. So this makes things quite challenging for forecasting and to know where it's going to be snowing the most. So time is now to investigate these things. So that's what we set out to do. A lot of the past work have identified a primary band, but as you can see from this example on the upper left, you not only have one region of high reflectivity, but there's always miniature, smaller scale regions as well. And this picture in the middle is actually a snapshot of an event that was actually here over Michigan, and it looks exactly like the one that we showed in our proposal. So it's like, it really does happen in real life, and this is a picture of one of the planes. So we went to investigate these different banded structures and ask questions: what are the vertical and horizontal structures, evolutions, how does it impact the snowfall, what are the processes, both thermodynamic, dynamic, and microphysical, what's going on in them, inside and outside. And there really hasn't been a really major field campaign on these East Coast snowstorms in over 30 years, so it was time to do it. We've been major advances in instrumentation, new modelings, etc., to investigate them, so off we went. So what we are addressing these challenges. It's a NASA-funded, what's called Earth Venture Suborbital. This is something that they make a call like every 5 or 6 years, and they fund the winning groups 5 years of funding. So we have 3 deployment years and a prep year and an analysis year. And with the pandemic, that's actually stretched to 6. So our main science goals are to characterize the spatial and temporal scales of snow bands, understand their dynamical, thermodynamical, and microphysical processes that control them, and apply this understanding to remote sensing improvement and modeling improvement of snowfall. So those are our ultimate goals. So how do we go about doing this? So a key aspect of this field campaign are the 2 aircraft that we are flying. So we have a very high-flying aircraft called the ER-2. It flies 20 kilometers, that's 65,000 feet or more, and we call it our satellite simulating aircraft, meaning the instruments that we have on that aircraft are very similar or almost exactly like what is often flown on satellites. So we have active and passive remote sensing instruments. We have both radiometers and radars and a LiDAR, and we actually have a lightning detection instrument that came on as a piggyback. So that's flying high above, and then underneath in coordination, so we try to fly one underneath the other as best as we can. They're flying at different speeds, so that's not all that easy. The P3 aircraft, and it has in situ microphysics and flight level environmental measurements and drop-ons whenever we're over the ocean. We're not, sadly, allowed to drop-ons over the land, and we couldn't convince them that if we just aimed for Lake Champlain, that we could just, no, that was not okay. So sadly, we had to only do drop-ons over the ocean, but that's okay. We still managed to do that, and you notice that the P3 is flying underneath, but at different altitudes. So that's something we prescribe every time we decide to fly in a certain storm. We just look at what the temperature ranges that are forecasted, and we decide based on that what elevations, what altitudes the aircraft should fly at. So it varies from storm to storm, but we don't ignore the stuff on the ground. We do have both stationary and mobile radars that were part of the field campaign, and mobile sounding teams and additional soundings that were launched by the National Weather Service. So the National Weather Service cooperated with us, and if we were going nearby one of their locations, like let's say over Stony Brook, and there's a OKX site there, we just, Jeff Wallstriker, please, can you send off a 15Z sounding for us and a 9Z sounding for us? And usually it was yes, despite the fact that helium is becoming harder and harder to come by. Now, Weather Service does have hydrogen in some particular locations, so they were able to accommodate us almost every time we asked for extra sounding, so that was really useful. I'm referencing an article here, so this figures in BAM's article that came out last May, and so there's a DOI there. And I want to emphasize that we have completed, so I literally just got back from the field just about 2 weeks ago. So we've completed our 3 deployments. So we've made measurements now over 3 seasons, winter 2020 and 2022 and 2023. So I thought I'd bring a couple pictures of what the aircraft looked like. So the P3's on the left here. It's a prop plane. Sadly, this picture, which is a beautiful sunrise, but the actual probes are outside the picture. So you have to look at these pictures here. So there's probes that are dangling down underneath the wings here and under there. And that we staged out of Wallops Flight Facility, which is on the eastern shore of Virginia. That's the home base for the P3. So that actually was very useful because if there's ever a problem with the airplane, they had a whole group of maintenance people who could fix it right away. And that came in handy multiple times because sometimes there's always problems with aircraft. The other aircraft, the high-flying satellite simulator, was ER2. It was staged at a different location every year for logistical reasons. And it's kind of like this albatross. It has incredibly long wings. And the instruments are very compartmentalized. So like this thing on there is actually, there's like 3 instruments inside this, I don't know what they call this, pod of sorts. And notice the nose, you could just open up, and there's the X-rad radars hiding in there. And there's instruments underneath. So they have like there on each wing, there's a pod on each wing with a nose and a belly. And the lightning instrument was these mills that were kind of scattered around the thing. And it's only operated by a single pilot. He sits up here. Where's my cursor? I lost the cursor. Cursor, how do I do this? Cursor is lost. Oh, there he is. Okay, back. So the pilot sits up there, and we have to communicate with him anytime we have any changes of plans of where we want to fly. He operates all the instruments, turns them on and off, and flies the plane all by himself. And he wears a spacesuit because we are up quite high, and you have to put oxygen in the aircraft, and it's a very complicated process. And this is a picture from one of the instruments on the inside here. I did throw in our ground team here. So the Raxpol radar on the top left here is from Oklahoma. They came in the last 2 years, and they did deploy a couple times. Skylar 2 is at Stony Brook, and this is a phase array X-band radar. And it does a volume scan, not RHI and PPI, but it just gets 3 dimensions all at once. I'm really amazed about that data. I still don't know how it all works. And then here's a couple of our hapless sounding team members. This one is very sad looking, but he actually is smiling under there. You just can't tell. Middle of the night, I'm in the snow, I'm happy, it's okay. And these guys, this is the Millersville team. It's hard to see, but this green thing, they pump up the balloon in there, and then they kind of lift off this cover, and the whole thing goes up. And when it works great. But they also sent me movies of when it all went awry. So, but anyway, they both, different sounding teams, we usually tell them where we want them to go, and off they go and make sounding measurements at all the same time. That coordinated with our, oh, I forgot that was a movie. Here we are, rotating. Okay. I wanted to use this graphic here to kind of get your head wrapped around like what parts of the storm do we typically sample. So this is a schematic of a mature mid-latitude cyclone, with a low center, surface low, and frontal boundaries, and these green areas of regions of precipitation with banded structures within them. Typically, we see these snow bands more or less on the northwest side of the surface low, but you also see banded structures on the northeast. So typically we are sampling in these two regions. But we also sampled near the low, not exactly down here in the southwest side, but somewhere near the low, and that's where you often see the smaller scale, more convective looking multi-band type structures. And down here in the warm sector is usually too warm, it's rerating or dry. The other part of this dry, or sometimes you get a dry slot that also works its way in here. It's that intersection, that dry slot and the moisture can be a region where convection breaks out, but it's very hard to sample because that dry slot is right where you decide you're going to fly, I can tell you. It's a nightmare. Yeah, yeah, that dry air. This is frustrating. So these are maps of where we flew. So I know that the graphics are not showing up on the screen very well, but I can point out. So 2020, 2022, 2023, and you notice that we flew, majority in the Northeast, but we came out here a few times. So I circled events that were in the Upper Midwest. Each year we sampled there, and this last year we actually came out here about 4 times. I have on the bottom the number of science flights. I didn't include I did on the last one, total number of flights. We did a lot of calibration flights as well this last year. That helped with our both our probes and the TAMS instrumentation. So 10 or 11 flights each year, and this last year we had the most coordinated flights. So these are flights where both planes were operating for an 8-hour flight, probably on station somewhere between 4 to 6 hours. So that many hours of coordinated information at 2 levels. So that was a pretty successful year considering it wasn't the very good year for the Northeast for snowstorms. Here's a list of storms. I'm not going to read them all. Just wanted to give you an idea. You can glance the different types, when the different aircraft flew. That was 2020. Here's 2022. I am going to talk about this one, a case that was over Chicago. In 2023, I had to make a smaller font because we flew even more. And there was this one I'm going to talk about, and these other ones that happened in later February. So February was kind of a good month for Upper Midwest, not just Wisconsin, but Michigan and Minnesota as well. So my goals today is just to give you a sense of the types of data we collected and show some examples, present their utility strengths and weaknesses, present my Midwestern events because I'm here in the Midwest, why not? And explore a range of science questions that we're addressing, but you're going to see we have more questions than answers at this stage. And encourage you all to consider using this data. This data is public, it's not mine only. It will be available, the 2023 data, which should be available by September. It's put in a public repository, and you go have at it. So the 2020 and 2022, most of these are already there. So let's talk about the Chicago snowstorm. So I have graphics of both, either we got in real time from the Tropical Tidbits website or my undergrad student has created from the ERA5 data. And John and I were just briefly talking about this a minute ago, this last winter we had a lot of positively tilted troughs. And this was actually from last winter, and this is also something that happened a lot last year, which is not as good for storm development. First, the low center won't deepen rapidly when it's a positively tilted orientation, but it doesn't mean you don't have to get snow. So I put the star here where Chicago is, and you see the vorticity max is kind of tilted in this southwest northeast manner. When you get closer down, you can just sort of see the red, that's frontogenesis. So right where Chicago is, there is mid-level frontogenesis occurring, at least from the ERA5 data. If you look at other models, they also identify that region. And at the surface, but it's kind of interesting, the surface low is fairly far south. It's way down here by Kentucky and Indiana, with a fairly good northerly branch throughout Illinois and a pretty strong southerly branch on the eastern side. And if we use the HER data sort of zoomed in, The wiggly squiggly things is, again, using the high resolution data to calculate frontogenesis. It is right over Chicago. And this shading is temperature advection. So it's kind of frontogenesis associated with cold advection, which often is kind of unusual. With that wraparound that I showed earlier, that's usually warm advection and frontogenesis associated with that. Again, this was a cross-section made in real time. And this is actually the AB on the upper right is where the flight line was. And you can see that the models at the time, this is what we're using this to plan our flights. Oh, it looks like we have frontogenesis. This blue is upward motion. We have a dendritic growth zone up there. We can fly this. Let's go. So off we went. So the soundings here, again, the numbers are, it's out of focus, but this is a typical kind of sounding, more or less. The same features are usually present whenever we are in a snowing situation. You usually have low-level cold air, and then some kind of warm nose, some kind of advection of warm air over the top. And that warm nose can be really too warm, and it'll be like rain, above freezing aloft, or not. So in this case, we had the sounding to the south, which was Purdue. Had a nose was above freezing in there, but to the north over Valparaiso, these guys did voluntary sounding launches for us because we happened to be operating there, and so they were just a little off of our flight line, but it gave us some environmental context here. And then depending on what's going on aloft, from after the top of that warm nose to the air aloft up to the troposphere, sometimes that is fairly more a steeper lapse rate. And when that is a steeper lapse rate, that can be more unstable. So you have mid-level, potential for mid-level convection or conditional instability up there. In this case, it doesn't look like it's that strong, so I don't think convection is a driving force here in this event. It's more, and you can see the shear, this is very strong northerlies and southerlies aloft. It's almost like a stationary front. So now I'm going to be, it's not bad, it's a little out of focus. These are our cross sections from radar from the ER2 on that line. So let me go back to that line. So we're kind of going from the warm side to the cold side towards Chicago, and this is what we're seeing. So the W band sensitive to cloud-sized particles, and it can attenuate when there's a very large particle. So the parts down here, you notice the reflectivity is lower. That's because it's all attenuated. But the structures that are kind of interesting here are right in this area. Notice how the tops are right underneath this really tall area. There's very narrow streaks. So they look like, I don't know if they are, generating cells, something on the tops of the clouds. And the dash line there, the P3, this is where the P3 was flying. We were trying to get cloud top. We were a little low, the cloud's way up here at 10 kilometers, but we still got features that are kind of cloud top-like. And in this region where you see those individual intense cells, you see elevated estimated liquid water content, and droplet concentrations went up. So they are correlated, but on the times on each end, out here, they're much lower. So that region is a region of sort of some kind of mechanism of generating more particles. And examples of the types of particles that we actually measured here are given below. You can see there's plates in this one, bullet rose. This is called a bullet rosette here. This to me looks like a caterpillar, but I'm not quite sure what it is. It's got these. It looks like a bunch of plates all stacked up.
It's a tardigrade.
Yeah, it's what?
Tardigrade.
That's could be what it is. Columns. So anyway, these are the blue is like the ones that are to the southeast. The green's like in the middle of that area, and this is these kind of crystal entities, I call them. They're like crystal aggregates, very complicated looking things. We see that all the time, and especially in these mid-levels, you don't know what to call them. They're just like a bunch of, looks like a bunch of plates that are formed off of each other and made a giant conglomerate, and they make a bigger particle. bigger particles have higher reflectivity. So that could be one of the reasons why I see high reflectivity. This is a different leg. It's going the same location, but it's later. It's like an hour later. We've gone up and then down. We're going up again. And here we see a little more intense. It doesn't look that intense using this scale, which is very broad. But this region has this fairly large peak, and you can't read that, but that says estimated liquid water, estimated ice water content. So the ice water content really jumped up there, and this one is drop size distributions, and by size, so how many are in each of these size particles, and you see that that also humps up. So we have more ice water content and larger particles that are concentrated, and I don't know, I actually put the line for the P3 a little lower so that you could see, I'm sure in the back you can see this little dot. Where is it? Cursor, where you go? Cursor, come here. Okay.
It's appropriately named, isn't it?
That's the P3. So we call it skin paint.
Oh, cool.
So, you know, radars originally were to monitor aircraft, and they do reflect quite well. And we're all excited when we see the P3 in there, because that means we are really, truly coordinated. Like, yep, we skin painted. That's usually a message that goes across the thing there. So, what kind of particles did we see here? So they got prettier at this level, a little lower down. Did I write the temperature down somewhere? Oh, there, -11. You can see on the right there some beautiful dendrites, and some that are, looks like there's two of them, kind of shadow casting on top of each other. And this conglomerate of God knows what's going on the one on the right here, knows what that is. So that is within this region of higher ice water content and higher drop size distributions. So the last leg, and I think this is a time where the Chicago air traffic control is truly hating us by now, because what's happening at the Chicago airport, it's snowing an inch an hour, and they're stacking planes up because they can't land, because they can't get the thing. And where are they stacking the planes? Over Lake Michigan. And where do we want to fly? Over Lake Michigan. And so we had to like plead, please let me fly here. And no, you have to go to a different level. How about this one? No, up that one. Oh, okay, fine. And promise to go home. Yes, we're going home after this. Promise we are. And so we were in their way, sadly. But interestingly, this narrow band, which I circled here, so to highlight it so you can see it in the back, even with this out of focus thing, it kind of developed over while we were out there. So when we were there earlier, it wasn't there, and now it is there. So what's going on in that? And we happened to go right across, just on the edge. They wouldn't let us we really wanted to be right over Chicago Airport. We really wanted to be right here. And not okay, so we had to be over there, but we did clip it. So on the middle panels here, again, this is from the downward-looking radar. The top is a KU band. So this is actually one of the radars that's on the GPM satellite is a KU band. The middle panel is called dual frequency ratio. It's a difference in reflectivity from two different banded radars, the KU and KA band. When the differences are large, they stand out like that big red spot. And then on the bottom panel, since it's a downward-looking radar, it's a Doppler radar, so we are measuring the Doppler frequency. And what we did here to make this pattern here is we calculated what is the mean velocity as a profile, so it's called a CFAD, and subtracted that out. So that profile is supposedly our estimate of the fall velocity of the particles. The bigger particles will fall faster, so you usually see that the fall velocity is faster lower down, and the smaller ones aloft are falling slower. Because we wanted to know what the environmental vertical motions were. That's a way to estimate that from the Doppler velocity. So, and then on the right is actually what's being measured by the P3. Again, the P3 is on this line here, goes right through this region of higher reflectivity in the KU band, higher DFR, dual frequency ratio, and some kind of moderate, not very strong vertical motions. But this is on the left, the mean particle size, And when I circle this, so there's the three features I was talking about in the middle panel. And then on the right, notice that there's a sudden jump up in particle sizes to go with that snow band. And then in this thing, you see that's estimates of ice water content, depending on which formula you use. You have to estimate that. So this one really thought it was a lot, so it's probably somewhere in between all that, but it's still relatively higher there than at other times. It's like hardly anything down there. So, and these are strips, you don't have to see what they look like, you just see that these are black blobs, that means there's bigger particles. And then that snow band, so that snow band, high reflectivity, looks like large particles, aggregation, bigger, in general, bigger sizes. So also outside the snow band is the red thing that you're pointing out. There was actually these pockets of vertical motion, but they're smaller particles. And smaller particles. And on the right, we see there. It looks like this. That's what this band. You guys see my cursor? I see it here. Why? There we go. These little dots is much smaller, and so we are hypothesizing that these are possibly supercooled droplets that's being measured. They're smaller features, so they probably don't have as high reflectivity, although there's water, so that's pretty higher. But we think that's being lofted by the vertical motions. John?
Are some of these differences, Lynn, this is really interesting, that the vertical motions where you have the band developing are weaker than in adjacent regions. Mm-hmm. But the volume of air that's involved in ascent is larger because the distance over which the air is rising is substantially bigger in the band area. So is it the volume of air that matters maybe and not the velocity at which it goes up?
Okay, $1 million question, John. I don't know. I think that's a good question. And that's something that we have not had anybody focus on right now to really, I think we need to document that in all our cases. And some of the issue is I like to talk about these snow bands, but it's very hard to define them. So in this case, where that circle is, we used an algorithm that, the definition that was put forward by one of the Brian Colley's student that required a certain length to, a ratio from length to width, certain reflectivity difference, all these little criteria. So we applied that criteria, and then you had to see, did it become a continuous area that was narrow enough to close it on the ellipse. So this ellipse was drawn by this automated algorithm. And we said, okay, that one worked. And there was another, we applied this to a different case, and the ellipse was so broad, it was just kind of this big area that, okay, is that a band? That's just a general rising. In that case, that volume is probably what's causing the vertical motions to make the particles to fall down.
Make them bigger. And then the other thing about a volume-based thing that's appealing is then you can separate scales of forcing.
Yes.
Because if it's a large volume of air, it has to be forced by something on the mesosynoptic scale and vice versa.
And vice
That's
versa.
neat.
Yeah. So, what you're going to see is there's a million things I can do with this data.
Yeah.
And we haven't done it yet. So we're just collecting them. Go ahead.
You said that the velocity figure you're showing, you've removed the mean velocity in each column. Could you clarify again? So
I did my hand waving. Velocity? Yeah, so it's a Doppler velocity, so the radar's looking down, so it's measuring, the falling particles, so and so if I showed you the raw, you mostly see everything down, because things are falling, okay? So we wanted to say, well, what can I have an estimate of the fall velocity of the particles? And if I know what that is, I can subtract that out and see what the background is. So if it's a big particle, but it's fighting up against a vertical motion, it's not going to fall as fast as you would think it is. So usually you take it over some piece of this whole leg. Sometimes you do the whole leg piece, you experiment with that, and you can come up with a distribution of velocities at each vertical bin, do some kind of bin thing. So you'll have a distribution of mean and some spread. So you typically see it kind of narrow down the bottom, and then it goes really wide at the top, and then I'm going to have no idea at the top of the clouds how fast the particles are falling because there's such a mixture of sizes, and so your estimate may not be that great. So that's what we did here. Whether it's the true environmental vertical motion is the question. And that's why that, what we do have on the P3 estimates of vertical motion from one of our instruments. So we did all the calibration flights to make sure we had good estimates of
Just for
vertical
the
motion.
nav data?
Yeah, so it's the TAMs, it's turbulent air motions, and I always forget what the second M is, but an S and whatever. So the TAMs, if you're familiar with that. We also have on that ER2 LiDAR, and the LiDAR, of course, gets attenuated at any distance into the cloud, so it's really mapping the cloud top. And so you see, like in certain regions, that we don't really penetrate that far. So like where that band was, I mean, you can see it better, like an example better, like here, right there. So it doesn't go very far, and other times it goes down farther. It's not too far again, but outside of it, you see that there is more variability in the cloud top, so that's probably generating cells. And I know a grad student is working with John Yorks, who's the CPL instrument PI, on looking at the cloud radar and LiDAR documentation of cloud tops in these systems. Because you see a lot of variability, but not every storm is like that. Some of them don't have much generating cells, so it's pretty interesting. Also for this case, we have, this is radiometer data. I'm only showing you very little of it. And the way this plot was made by Rachel Proxma, each of these is a different leg. So she put time like this. So I believe this is, I think it's forward looking and scaling like this. And it's going up. And she's spread this out. So you can actually see the development over time of the cloud features. These wavelengths that are being measured at 165 gigahertz and 183 are mostly sensitive to the clouds. You actually don't see the ground. And she showed me her 89 gigahertz, and you can see exactly where we crossed the lake. So we know we're not looking at the lake there. So I just circled at the very end is that wasn't there before, and then it became later. And when you see the colors that are lower brightness temperatures, that is sensitive to ice. So there is a signature in this radiometer data of the ice cloud developing over time. So that's a really cool thing. So I wanted to remind you about this DFR. I wanted to show that we do have a paper that's published by my postdoc, Joe Finland, looking at the DFR signatures, this difference in reflectivity at two wavelengths, the KU and KA, and inside a high DFR and outside that has low DFR, and relating that to different microphysical properties. So we do see, so these are different events in 2020, so he did this with 2020 data. So the DFR is the solid lines, and dashed lines is out a low DFR, not much difference. And you really do see that the DM, which is this plot, always bigger particles on average. These are box of whiskers, so the solid means are much higher, especially these last three, which are much more snowing events. The first two had more rain. We have smaller effective density. It means like they're aggregates with holes in them. So if it's a dense particle, it's got, it would be a higher value. So it's the opposite sense. And smaller numbers. So you have fewer numbers of particles, but they're bigger. Fewer but bigger with big spaces in them are related to high DFR. And the liquid ice water content, there's not any significant difference. And we want to test this within other 2 years of data. So he's working on that now, and we hope to get a follow-on paper on this. But this DFR signature is actually really useful for remote sensing. On a satellite, we don't have any probes, but we have radar reflectivity. How can we use that to deduce microphysical properties? So this is one avenue to pursue that. So I'm going to have to fly through this, but this is a recent event, February 2023, another positively tilted event with this 250 hectopascal streamlines and isotachs here with the low center. And then there's a nice vorticity max right over here. And we actually flew over Michigan, in this region in that area. So if I go a little closer. It's a good thing this is, you can't read it because it's like a mess of a surface analysis.
Yeah.
Pick your favorite. I think, you know, they did okay with the main low, the cold front, the warm front, but God knows what they're thinking with these other fronts. There's probably, I can give them excuses, probably pulses of cold air coming down. There's no wind shift whatsoever. God knows why they call it a front. But this is a case where you see the shading you can see here is frontogenesis, mostly associated with warm front and occlusion front, kind of an arching band, kind of deformation zone to the north. So that's kind of the background. It was over Michigan that we flew. You can still see like there's a lot of modeled structure to the clouds here. Michigan, Central Michigan, University of Seneca, Wayland Soundforce, and Gaylord did too. So these soundings are here on the right. Similar structure. It was raining sadly at Michigan, Central Michigan, but it was all below freezing at Gaylord. Again, this case doesn't have as much conditional instability aloft. So yeah, go ahead.
The coloration reminds me of, I think it was this storm, and there were two this year, and I don't know if it was discussed in Weather Watch, but here's a ground unit. There was definitely a lot of yellow dirt in that snow, a lot.
Yellow
and I was
dirt?
wondering if you can see that with your instruments at all. It, you know, detection
Yeah,
of low
you would think
mineral content.
you don't have
Does anybody else
aerosol
notice
information.
that?
I don't
That storm.
remember. No, I know people
Or
do.
did you
I
back on
noticed it.
weather
I
guys?
don't think I saw it.
Yeah,
Yeah.
Yellow dirt.
it was. Then there was another one earlier this year in December.
Yeah,
So
so it's
probably
perfect
tracking, you know, dust from
from the southwest.
From the southwest.
Yeah.
There was another event on the
We'd have to
East
go all the way around.
Coast. Yeah.
Huh.
I don't have aerosol instrumentation. I did not. Can't
Surface
do that.
surface.
Other ones can do that. So,
It was just so striking.
yellow
Never
dirt.
seen it.
Okay, cool. Again, the cross-section is similar to before. You have sloping chronogenesis. In this case, the relative humidity was such that the northern portions were forecasted to be deeper, so we have a lot of, and then a nice dry slot, not so nice to me, but that's what was happening a lot, and this purple is vertical motion. So sadly, this is one of the times with the ER2 couldn't fly, because with that nice storm going on over Michigan, it also has a cold front down here, and we were out of Georgia, and it was a convective line, and the ER2 cannot take off in that kind of conditions. Plus, the winds were cross runway, and if you remember seeing that huge long wingspan, it can't tolerate crosswinds. So they were out of limits. We weren't allowed to take off for the entire flight. So we're using here, so these radar pictures are from the NextRad. They're gridded data, pseudo kind of RHI, so it's not nearly as detailed as what we got from, or we could get from there too. But I wanted to show you that this is where you see a lot of tiny scale, almost micro scale structures. There is banded structure here, and that red diamond, you can see the difference. So each of these diamonds relates to where I think these sample particles came from. So on the north side is a crystal entity. These are billet rosettes with caps on them. So those are kind of cool pictures. Wonderful little star, dendrite, and this agglomeration thing in the middle of the snow band, and then some more interesting things on the right there. That same area, we did have a spike in estimated ice water content associated, even though the band structure is lower down, we're flying up here, but even aloft, there is a signature. So stuff, like the trouble with these ice, these lines, what is hitting the ground, it may not be from above, it might be from over here, it came in here, but then you have to make this assumption, maybe I can assume a little bit of uniformity in other directions, or just hope to God that it works. It seems to, at least the story hangs together. You see estimated water content, ice water content is higher, again, with a drop size distribution, big bump, so there's bigger, more of the bigger particles, and here they are, the big particles. So that relates, it's kind of similar story. I just want to show you that What I showed with the Chicago storm also occurs with other storms. And it's not unique to the Midwest. The East Coast storms had the same kinds of signatures. So it's just kind of fun to show you the different kind of particles that we observed. And one theme that I saw over and over again, the ones on the right here that were under again, I forgot to put the circle here, but that's the snow band, and even south. Notice these are darker. Those are rimed particles. So you had some kind of, you can't even tell what it used to be. Maybe it was a dendrite, God knows what it was. And then it falls through a layer of supercooled water, and it's all adhering to it. It's like it's got a bad case of the measles or something. And even on our probe that usually does pictures of this, picked up almost all droplets. And that's what's on the right. Those are supercooled drops that, it looks like we're in the clear, but this gridding algorithm doesn't really tell you exactly where the cloud top is. We were definitely in cloud there, but it was above this enhancement down here. So this wiggly, this is a signs of sublimation. We don't have the sharp edges anymore. And that was actually in between this turret and that turret. It's like right here, what was down, maybe it's downward motion, I don't know what's going on there. Some dry air snuck its way in, sublimated just that one little guy, so who knows. Again, that supercooled water is something that I really want to investigate for these cases, these storms. It happens a lot. It often happens more preferentially in what we define as a band. These probes here, this is called, I can't remember what the RICE stands for, but when it shows fluctuations, it's actually reacting to supercooled water. It's not just water, but supercooled water, and that's when you see that, and that was happening right at this time. The King probe measures liquid water, and it also has a peak there. And I flipped this out here, but I kind of regret it now. I'm trying to show from our flight level data that we actually went through a strong wind shift right during that area. We had northeast winds to the north and switched to the south at the level, and we're at, looks like 3 kilometers, so about 700 millibars. We're seeing actually a fairly sharp wind shift that happened along our line. So the supercooled water is an important feature. Now this is lower down. Each one of these is, the P3 is flying lower and lower. And now we're getting pretty far down, 2.5 kilometers, and all this rhyming happening inside this band that's starting to form here. That's all these rhyme guys. Also sublimation on the very edge. And then needles down in here on this side. This is the side is probably raining at the surface underneath these guys with supercooled water and needles. And so I'm kind of running out of time, so I'm going to like zip through that. And only showing this because I just have to show the pretty pictures, okay? Just indulge me. I love these dendrites with measles here. these guys here. And they're mostly inside actually the two on the left are in the bigger band, and these other ones are in the smaller band to the south. You can't even make it out in this plan view where where those enhanced regions of reflectivity are. So it's down in here. So that's really cool. So I wanted to kind of go back to our science goals for a minute. We were trying to characterize and understand the snow bands, and the examples I showed today kind of are addressing that. Clearly we don't have all the answers. There's a lot more questions. There's a lot of studies going on. But I did want to show a couple of apply ones. So there's a paper that's Colloquium et al. Is in review. I'm the one who's holding it up. And it was hard to come up with a good figure. So what Colloquium et al. Is doing is we're looking at the modeling application. We have direct measurements of microphysical properties. We have models that have microphysical schemes. How well are they matching? And what we're finding is they're not matching that well. And on each of these sets of bar plots, these are, again, what the observations are in black, and each of these other ones are different, either model runs from WRF using a different scheme, or a different initialization time, or a different initialization grids. And sometimes they're okay. But this one's really bad. Each set is from a different level, so we were matching it at the different levels that the plane was flying at. And sometimes what happens is you're right for the wrong reason. You can have, when you find at the ground that the measurements that the model produces, oh, that looks pretty good, it matches what I'm getting at the ground, but when you look up in the sky, it's like, oh, that's not, it's right for the wrong reason. So the ones that match well, they didn't have the microphysics very good, but they had stronger forcing than what we actually observed, but that was then made up for the under prediction by the microphysics, and in the end, it all looked okay, so we thought it was good. So we have a lot of ways to go. This data that we're collecting, we can do a lot more with verification and a lot more experiments. So we are applying, we're doing this, we're addressing our goal of applying this to modeling. And I wanted to highlight, this last year, we had a new radiometer that's a sub-millimeter wavelength. That said millimeter wavelength, I meant to say sub-millimeter wavelength, I think. And again, that same idea where each leg is subsequently a later time. And what it's showing is the development of that banded structure with time. So this is able to map out how that cloud feature, in this case, the wavelength that we're looking at seems to be sensitive to the banded structure. We actually see it dissipating. It was stronger at the beginning, and it got weaker and weaker. So the greens and blues are lower brightness temperatures. And then these wavelengths are, I have to read it here for you, they're like 385, God knows what they're really small. I can't see it on that screen. It's all really bad. Okay, 325. We're seeing the middle part, the upper part of the cloud from this radiometer. So that's kind of a new feature. And it was a brand new instrument. We didn't even test fly it because we had problems with the plane. And we just threw it on, sent the plane out there, and it worked the entire season. Kudos to the engineers. So anyway, I wanted to summarize here. Impacts was a multi-year field campaign to observe snowstorms. I wrote looking forward to 2023 because I used the title from a different slide. But we did 2023, so we have over 35 storm events that we have sampled with coordinated observations for most of them. I showed you 2 Midwest events just to highlight that, and there's many ongoing studies happening by the team members. And one thing I want to say, the data are posted to the DAC. If you want this webpage, just ask me and I can send it to you. You can go right there and you can get the 2020 data, 2022, much of it's there. 2023 will be posted by September, and we'll have a data workshop in the fall to, anybody who's interested to learn more details, because you really want to hear from the instrument PIs about do this but don't do that with the data. There's certain caveats. We do have field catalogs for each year that we were up in for each deployment year. The links are there. This is a thank you to my entire team from our science team meeting last summer, but I wanted to leave you with our collage that one of our forecasters puts together for the last day. But then he sent me this one. So he said, this is what we should use for 2023. So he's invented a new name. It's investigating microphysics and precipitation for Upper Midwest and Canada threatening snowstorms, because that's where we flew. And a puma, so that's a puma. And then he made an 8-pointed snowflake. So this is what happens when you read the field too long. So I'm going to go back to that one. So I thought you guys might appreciate the Pumax is what you should be calling us for the 2023 deployment. So with that, thank you very much.
Couple questions from students first.
Don't be shy.
Julia.
So I have a question with the radars. What's like the resolution on them, like the range resolution?
Oh, like vertical?
Yeah.
God, I don't know numbers off the top of my head. It's very high though.
Okay, because I was thinking about the DFR type looking at microphysics with the GPM, DPR, with having the two frequencies. Is that range resolution like too coarse, to be able to look at that kind of stuff?
I think you can still use that, let me see if I can find that figure.
Because that's used for detecting melting, right?
Yeah.
But I'm not super familiar with it, that's why I'm asking.
So, so this little blob in this case of high DFR looks like it spans a couple of kilometers. And, you know, we have a lot of resolution here. So again, I don't have the numbers here, but, you know, meters, I don't know what it is in meters. So it's actually quite fine. So, I'm sad that this is out of focus for you guys because my screen, it's like, I don't know, when I connect it up here, you change things. You see there's fine details in there. So, but from a satellite, from GPM, you don't have that same vertical resolution, but if that signature is deep enough, I think you still would be able to use that. And that was part of the motivation to look at the DFR, because that is something that we can do now with the GPM data. So, and this also kind of tells you that I think there's a lot of usefulness to have those dual frequencies. And they are planning a new satellite, and there's a possibility they won't have the dual frequencies, so there's a lot of not so happy people about that. And there's this, you know, they can point to this study and show, and this and others, there's other people looking at this in other circumstances as well. So I don't have the exact answer for you, like I don't remember what the resolution is, but I think with a 2 kilometer deep feature here, that easily you should be able to see that from satellite. So I think you can easily.
I'm just curious about the formation stage of these structures.
Mm-hmm.
Like, do you find that there's evidence of something different spatially in the cloud particles or the precipitation particles that precedes the formation of the band?
Oh, wouldn't that be cool? I don't know if I have, you know, it's hard when you're flying, when your main way of measuring the storms is from aircraft, is you're limited to how many hours you can be out there. So the whole snowstorm, you know, maybe lasts a day and a half. I am not flying continuously for a day and a half, so I may not catch that formation stage.
Sure.
So we had a lot of questions whether or not we caught that. The Upper Midwest cases that we tried to fly in this year, we were trying to get to that developing stage. And sometimes you see these features that are very small scale, initially near the low, and then, you know, the flow patterns around it, they kind of merge a little bit into a larger banded structure. So I think that's a great question. I don't know if I have, you have to only look at it statistically and see if you could figure out, did we actually sample enough early stage versus mature stage.
Sure.
And I don't know if I did that, to be honest. Especially the prior 2 years, we tended to be a little late to the game. We were there when the bands were pretty well established. So I saw them dissipate this year. That was great.
Sure.
Dry slots, gets rid of them quickly.
So I guess I'm interested if you think it's like a positive feedback among the particles themselves or something dynamical.
Yeah.
Or maybe both.
God, I wish I could tell you one or the other. I can see arguments for both. You know, the life cycle of the storm will have a period of the most intense deepening rates. Usually it's because that's, you know, the time that the baroclinicity is strongest and the vertical motions are strongest. And I would think with that environment, you know, with good strong vertical motions, that allows for, you know, for condensation and also allows for deposition and aggregation to happen. So that would accelerate these processes.
Sure.
There is a student who's at UIUC who's doing some idealized simulations, and he's simulating generating cells. So he actually starts out with like this grid of dots of particles, and then he puts it into a shear flow, and they tend to organize into bands. So it's that shear environment. So these, especially the more stronger events, have a lot of shear in them. So especially the good nor'easters would. And I think he actually used we had a really good nor'easter last year. He used the environment, the synoptic scale pattern for that, the shear environment, and he managed to get banded structures out of initiating out of generating cells. Lots of assumptions to do that, but it's a very intriguing study that he did.
Cool.
That is
Thanks.
cool.
Just after 4:30, so we'll do one or two more questions and then encourage folks to stay after.
Yeah,
chat with
you
Lynn.
can
Yeah.
chat all you want, I don't mind, yeah, go ahead.
Yeah, go ahead, John.
It's so many interesting things here, Lynn. I really was intrigued by the disjuncture between what you're observing in the microphysics and what you predict with the models. And this is a real big problem, especially though you put it in the right context. You can still get what looks like the right answer at the ground.
Yeah.
But what's wrong in the end in your whole column? Is the latent heating wrong? And therefore, how does that feed back into structures and maybe then into dynamics?
Yeah.
I mean, is there a way to trace that back? That's one question, and you don't have to answer it. I just wanted to highlight it. It's so interesting. But another one is, with all this talk about supercooled water, do we know what the landscape of supercooled water in and around a mid-latitude cyclone is? Because what if that's the background condition
It is.
upon which other things add and then start to form bands because of that?
I
Seeding.
think that's one of the questions I'm really anxious to get after. We have a lot of events. I mean, every single event has supercooled water that was sampled. And when we had one, we actually had one in Minnesota go, God, where is the supercooled water? There is no supercooled. What's wrong with this storm? There is no supercooled water. Why not? So almost like there's one that doesn't have one, which is actually cool.
Yeah.
And then our last storm this year, we flew on February 28th. All we had was supercooled water. We're going, where's the ice? Why is it snowing on the ground? Why can't we seem to find it? It's all supercooled water. We were like so confused. That was right offshore of Long Island. I think one of the problems is that we were chasing and we didn't do a good job of actually hitting where we should have been. And over the water, like over the Atlantic, that kind of water, lots of supercooled water is available. I think these supercooled water seems to be where there's local regions of vertical motion. So you see it a lot of the cloud top generating cells. There's always a lot of supercooled water at the top because they are small overturning cells. Bob Roberts' hypothesis is with radiational cooling, making little environment, and also that if you have that mid-level of instability, that's also overturning, in addition to the synoptic scale of vertical motion.
Yeah.
So we see a lot of supercooled water off the Washington coast and over the orography, and that is enhancement from lifting over the mountains. So you're taking a moist environment, just throwing them.
So it's vertical advection of pre-existing water droplets
Perhaps,
in that
or
theory.
forming it. You're forming it through.
In a cold enough updraft.
Yeah, like an updraft. An updraft that.
It's just weird.
That, and with CCN, we have to have CCN available too.
Yeah.
And CCN's pretty easy to find compared to ice
Yeah.
particles. There's probably ice, multiplication processes going on. Hard to document. We think we have that. Somebody's got to be clever to piece that out of the data. So, yeah,
Very interesting.
lots of
Thanks.
good questions.
Last question, Grant, go ahead.
I know your focus is on snow bands
Yeah.
and on the structures and
Yeah.
microphysics and so on, but one of the things that's often struck me about some significant snowstorms we've had over this area is sometimes you look at the radar and it's absolutely lacking in any structure whatsoever. It's a uniform veil of moderate snow over the entire state. And you can't find a band anywhere in there, and it almost seems like something must be suppressing structure.
Yeah.
Did you encounter anything like that during your flights, and did they look different from a dynamical or stability point of view?
I might go back and look at that, look for that. So the storm that Brian's paper in Colloquium, where is it, the February 7th case, he has it in his title like a non-banding event. You gotta find it. Well, I don't have. Oh, I actually have. I do have it somewhere. It didn't show this. Aircraft full over snowman. Well, it's broad here. I made a circle too, but and this is bright banding here. So this is the aircraft, and this half is all snowing. Sometimes you see it. It's just it's not narrow enough to be called a band. It's just broader. So I'm wondering if deformation is weaker, or phreноgenesis weaker. So, phreноgenesis is usually tied to from the deformation zone. So maybe you have some broad scale uplift and lack of deformation to bring things together and then stretch it this way and make it into a band. That's my hypothesis.
As good as any.
Good as any, I know. Otherwise, it's just snow happens. Who knows? But it's a good thing to look for. Like, what's the strength of deformation in all these events? Is that exactly where we see the bands? Because I bet you we don't always see it there. But I think we see most of the time we see it there.
All right, let's thank Lynn again.
Okay, thank you.